Tonight, you and I are alone in a lab that's gone quiet enough to hear the computer fan arguing with the silence. On the monitor, a sky map, every galaxy, every filament, every void, flattened into pixels like a scanned photograph of reality. And the question that sneaks up on you at 2 a.m. is almost embarrassingly human. If you just keep going, do you ever reach the end? Not the end of a road. Not the end of a semester. The end of space. The place where, there, stops being a meaningful word. Because somewhere in your life, maybe on a long drive at night, headlights pouring into darkness, you've had the thought, if I never turned around, if nothing broke, if time didn't run out, would I hit an edge? Would there be a wall? A cliff? A sign that says, beyond this point, reality is closed. Now aim that exact feeling at the universe itself. Here's the strange part. Physics doesn't let us step outside the universe to look at it the way you'd hold a globe in your hand. We're trapped inside the thing we're trying to measure. We're like sailors trying to prove the Earth is round without ever leaving the ocean. So tonight, we're running an audit, not of opinions, not of intuition, but of what the universe has actually allowed us to observe. And when you ask, does space go on forever? The answers people imagine tend to fall into a few buckets. 1. It's infinite. You keep going forever, no matter what direction you choose. No edge. No return. Just an unending more. 2. It's finite with an edge. Space ends like a room ends. Most physicists dislike this option not because it's emotionally unsettling, but because it's logically messy. If there's an edge, what's beyond it? And if you say, nothing, what does that even mean physically? 3. It's finite but unbounded, limited in total size, but without any border. Like the surface of the Earth. You can walk forever and never fall off, yet Earth's surface area is absolutely finite. It's the first mind twist. Finite does not have to mean walled in. And 4. It's wrapped or repeating. Like a video game map that looks flat and endless, until you walk far enough and suddenly you're back where you started. Not because you turned around. Because the map itself is stitched together. In physics language we call that a non-trivial topology, but let's keep the metaphor. Reality could be tiled like wallpaper, or looped like a donut, in 3 dimensions. So which one is it? Here are the audit rules. We can't go outside. We can't shine a flashlight from beyond the cosmos, and watch it bounce off the edges. We only get internal evidence, how light travels, how geometry behaves, and the patterns encoded in the oldest light we can see, radiation left over from when the universe was young enough to still glow. If space loops back on itself like a video game map, it should leave fingerprints. Not in a mystical way. In a brutally physical way. Light would have paths. Patterns would repeat. The universe would, in a sense, double print parts of its early history on the sky. So let's begin where every honest cosmic investigation begins, with what we can actually observe. Imagine pulling away from Earth. The lab vanishes. The planet shrinks to a marble, then a pale point lost in the glare of the sun. You keep zooming out, past the outer planets, past the Kuiper Belt, past the thin shell of comets, past the local stars. The Milky Way becomes a luminous smear. Then even that dissolves into a crowd, galaxies and clusters, clusters and superclusters, a cosmic web of matter stretched like frost on a window. And then something subtle happens. No matter how hard you try to zoom out, there's a limit. Not because the universe ends there, but because light has a speed limit. The universe is about 13.8 billion years old, and light has only had 13.8 billion years to travel. Even accounting for the universe expanding while the light was in transit, there is a boundary to what we can see, the cosmic horizon, the edge of our observable universe. This is a crucial distinction, and it's where people get tricked. The observable universe is finite by definition. It's the region whose light has had time to reach us. That finiteness does not automatically tell us the whole universe is finite. It tells us our view is finite, like a flashlight beam in a dark field. So the question becomes sharper. What does the geometry inside our flashlight beam say about the whole field? To answer that, we need a word that sounds like pure math but is actually something you can feel: curvature. Curvature is what separates a flat sheet of paper from the surface of a sphere or a saddle. But you don't need to imagine the sheet bending into an extra dimension to understand it. You can detect curvature from within the surface itself by doing measurements that only require rulers and angles. Here's the metaphor that makes it visceral. Draw a triangle. On a perfectly flat plane, the angles add to 180 degrees. That's not a rule of triangles, it's a rule of flat space. On a sphere, like Earth, draw a triangle with lines of longitude and the equator. You can make a triangle whose angles add up to more than 180 degrees. Positive curvature. Space bulges in a way that makes straight lines converge. On a saddle-shaped surface, triangles can add up to less than 180 degrees. Negative curvature. Straight lines diverge, like paths that keep fanning apart. So when cosmologists talk about whether the universe is flat, positively curved, or negatively curved, they're asking, what do the biggest triangles in the cosmos tell us about the geometry of space? But then comes another twist, because the universe isn't a static stage where matter moves around like actors. The stage itself stretches. This is metric expansion. Distances between galaxies grow not because galaxies are sprinting through space like fireworks, but because space between them is swelling. A helpful metaphor is rising bread dough with raisins inside. The raisins aren't all propelling themselves away. The dough expands and the distances increase. That means, going straight through the universe isn't the same as driving through a fixed grid. Space itself participates. It stretches, it changes the rules of travel, it changes how light accumulates time. So what have we measured? We've measured the curvature of the observable universe, and the current best results say it appears extremely close to flat. Within our measurement limits, triangles add up to about 180 degrees at cosmic scales. Parallel lines behave, to the best of our ability to check, like they do on a plane. Now, close to flat doesn't mean we've proved infinite. It means if there is curvature, the radius of that curvature is enormous, far larger than our visible patch. Imagine standing on Earth, but your entire observable world is a few meters across. The ground looks flat. It really is curved, but the curvature radius, Earth's size, is too large to detect from your tiny neighborhood. So flatness is a clue, not a verdict. And this is where we have to separate two ideas that people blend together: geometry versus topology. Geometry is local. It's the rulebook for how distances and angles behave in your neighborhood. Is it flat, spherical, saddle-like? Topology is global. It's the question of how the entire space is connected. Are there shortcuts through the fabric? Does a straight path eventually return? Is the universe glued to itself in a way that creates loops? A world can be locally flat and still be globally wrapped. A video game map can feel like an infinite plane under your feet. Every small patch is flat, but the edges might be stitched together so that walking far enough brings you back. So if the universe is close to flat, it still could be infinite. Or it could be finite but unbounded. Or it could be wrapped like that video game map. Flat geometry does not settle the global question. And when you realize that, something almost emotional happens, because you feel the floor drop out beneath your intuition. Now slow down with me, because we're approaching the frustration at the center of this mystery. Flatness doesn't decide infinity. You can live on a perfectly flat grid and still be trapped in a loop. Your ruler won't complain. Your triangles will behave. And yet the world could still be finite, because the finiteness isn't in the angles. It's in the wiring. So let's do a thought experiment so clean you can almost smell the night air in it. You are an ant on a vast, smooth surface. It's night. There's no sun, no stars, just darkness. You have a flashlight strapped to your head. It illuminates only a limited horizon. Beyond that circle of light is pure unknown. You start walking. The ground under your feet feels flat. If you draw triangles inside your little pool of light, you get 180 degrees. So you announce, the world is flat. But what you've actually proven is only this: your neighborhood is flat. You have not proven that the world is infinite. How would you detect that your world loops? You'd need repeated landmarks. Or you'd need to measure geometry so precisely, over such long baselines, that tiny deviations would betray a global curve. And now, this is the move: replace the ant with us, the flashlight beam with the observable universe, and the landmarks with patterns in the sky. What are the candidate worlds we might live in? Let's tell them as places you could inhabit. One possibility: a 3-sphere. Not a sphere in ordinary 3D space, but the three-dimensional analog of a sphere's surface, finite volume, no edges. If you travel far enough in a straight line, in principle you come back, but you never encounter a wall. Another possibility: a 3-torus. This is the video game map idea made cosmic. Imagine space is like a cube whose opposite faces are identified. Walk out one side, you re-enter from the opposite side. Do that in 3 dimensions. Locally it's flat. Globally it loops. Another, infinite Euclidean space. The simplest, an endless, flat expanse. No return. No stitching. Just unbounded extension. And then there are more exotic compact spaces, strange ways to fold and glue space that still keep it finite without edges. Nature is not obligated to choose the simplest topology our brains can picture. So how do we audit these possibilities using only internal evidence? We use light, because light is the universe's record keeper. The most important light for this question is the cosmic microwave background, the CMB. It's the afterglow of the early universe, a faint bath of radiation coming from all directions, emitted when the universe cooled enough for atoms to form and light finally traveled freely. You can think of it as the oldest photograph we can ever take, a baby picture of the cosmos. And if space wraps, that baby picture might contain repeats. Audit tool number 1: match circles in the CMB. Here's the idea, in plain terms. If the universe loops back on itself, light can travel around the loop. That means we could end up seeing the same region of the early universe in different directions, like seeing the same mountain reflected in multiple mirrors. On the sky, those repeats would show up as matching patterns along circles, pairs of circles with the same temperature fluctuations, the same speckle pattern, because they're literally the same physical patch of early universe viewed along 2 different light paths. So scientists looked. They scanned the CMB with satellites like WMAP and Planck, hunting for those matching circles. It's painstaking, pattern recognition on the largest canvas imaginable. And what did we find? No obvious matched circles at large angular scales. That doesn't prove space doesn't wrap. It means, if it does, the wrap length is likely larger than the diameter of our observable universe, or the specific topology is subtle enough that the signature is below our detection threshold. The mirror, if it exists, is too far away to catch in our flashlight beam. But we don't stop with one tool. Audit tool number 2: large-scale modes and missing wavelengths. Think of the universe like a musical instrument. A guitar string can't vibrate with a wavelength longer than the string itself. The finite length sets a maximum pattern size. If space is finite, it similarly limits the largest possible waves of variation in the density of matter and radiation. That would show up as a suppression of the biggest patterns in the CMB, less power on the largest angular scales than you'd expect from an infinite space. There have been hints and anomalies, oddities at large scales that make people lean forward in their chairs. But here comes the humility clause. Audit tool number 3: cosmic variance. Cosmic variance is the universe reminding us that we only get one sample. We don't have a shelf of universes to repeat the measurement. We have one sky. Some of the largest scale patterns are fundamentally hard to interpret because there are so few independent modes to average over. It's like trying to judge the fairness of a coin after only a handful of flips. So when we see a large-scale anomaly, we have to ask, is this the signature of topology, or just statistical happenstance in the one universe we inhabit? And now, right here, is the moment where the whole mystery changes shape in your hands. Because the real revelation isn't, the universe is finite, or, the universe is infinite. The revelation is this: an edge is not required for finiteness. Finite doesn't mean walled in. It doesn't mean there's a border where the laws break. It means the geometry and the connections of space are globally self-consistent in a way that gives it a total volume. Like Earth's surface, finite area, no edge. Like a looped map, finite tiles, endless walking. Once you truly internalize that, the question stops being, Where is the edge? And becomes, what is the wiring diagram of space? So where does the audit land honestly today? Here's the straight report. We have strong constraints. The universe appears very close to flat within measurement limits. We see no clear repeating sky patterns, no unmistakable matched circles, at the largest scales we can test. That pushes the possibility of a small, wrapped universe farther out. But it does not close the door. Several topologies remain possible if the wrapped scale is larger than what we can see. If the universe is a looped map, the scene might lie beyond our cosmic horizon. The stitch could be real, and we would still be unable to find it, because the light simply hasn't had time to complete the loop and report back. And that's not a failure of imagination. It's a fact of being embedded in time. Now let's bring this home, back from the cosmic web to the private, human feeling that started this. If the universe is infinite, then somewhere is not just far. It's unbounded. It changes how you think about rarity. In an infinite universe with enough randomness, events that seem impossibly unlikely here might occur elsewhere, not because destiny repeats, but because infinity is a ruthless amplifier of possibility. Your uniqueness becomes a statistical question, and that can feel either terrifying or strangely comforting depending on what you need from the night. But if the universe is finite and unbounded, reality is less like an abyss and more like a planet. Total volume, no border. A closed book you can walk through forever without finding the cover. The cosmos would be complete in a way that doesn't require an outside. And if space is wrapped, if it loops, then distance becomes political. Direction matters. A straight path might be a return path. The universe could be a hall of mirrors where light comes back to you, not because it bounces off anything, but because the map itself is glued together. In that kind of cosmos, the phrase, far away, hides a deeper truth. Far away might still be nearby in the global sense, like the other side of a stitched seam. You could, in principle, be looking at your own galaxy's ancient light from a direction you'd never suspect, seeing a younger version of home, because the long way around is still a way around. And now the philosophical landing, the part we usually avoid because it sounds too soft for physics, but it's actually the reason we do physics at all. Our instincts were trained in rooms with walls, on landscapes with horizons, in lives with endings. We carry that architecture into our questions. We keep asking, where does it stop? But the universe might be the first place we've ever lived where, end, is the wrong question, and connection is the right one. Not where does it terminate, but how does it join? Not what lies beyond, but what lies around. So here's the synthesis, clean and unsentimental. We asked whether space loops back on itself like a video game map. We found that the observable universe is finite, but that doesn't decide the total. We learned that geometry, curvature, seems very close to flat, but flatness doesn't rule out a wrapped topology. We saw the tests, matched circles in the CMB, missing large-scale modes, and the hard limit of cosmic variance. And the audit result, for now, is no decisive evidence of a loop within our observable horizon, but no definitive proof that the greater cosmos is infinite or unwrapped. The door to a finite, wrapped universe is not closed, just pushed farther out than our flashlight reaches. Now let's end with a thought experiment you can carry into tomorrow, because this question isn't just cosmic, it's personal. Imagine you could fire a single pulse of light in a perfectly straight line, in a perfectly known direction, and you could wait as long as necessary. If the universe is wrapped tightly enough, that light could return, arriving from behind you with the timestamp of a much older world. You'd be holding a message from your own past, delivered not by time travel, but by topology. What would it feel like to receive proof that forward eventually becomes back? That the universe doesn't end, it connects? And that opens the next great question, the one that's almost uncomfortable to ask. If space can loop, what else about reality might be a matter of hidden connections rather than boundaries? If you want to keep going, click the video on the end screen, because it takes this same audit mindset and aims it at another place where our intuition breaks. And if you want a reason to subscribe, here it is. We don't do science as trivia here, we do it as a careful, human investigation into what reality is allowed to be, one test at a time. Now I want to hear from you. If you could run one cosmic experiment with perfect precision, one measurement the universe couldn't hide from, What would you test to decide infinity versus wrap? Keep it simple, name the measurement, and tell me why you chose it. I'll be in the comments reading every theory you bring back from the edge.